Okay, back again. This is again 24.6-3. We're going to start with the Hofmann rearrangement. We take an amide, primary amide. It's treated with sodium hydroxide, Br2 in water. And we end up connecting the R group to the NH2 group. So our amine product here, which is what we're interested in this chapter, is the primary amine, and of course we end up with CO2. We can make all sorts of amines with this, both alkyl and aryl. So let's just take as a simple example here this phenylacetamide. If you treat that with sodium hydroxide, Br2 in water, then you end up with loss of one carbon as CO2. So that's the Hofmann rearrangement. So we take the amide, sodium hydroxide, bromide, and water. Then there's a related one, the Curtius rearrangement. Okay. All right, I'm going to present the Curtius rearrangement slightly differently from your textbook. I'm going to start with the acid chloride, which we can treat with sodium azide. Azide we learned about in the amination of amines a few videos ago. This produces this acyl azide. Now I'm going to draw out the azide. That acyl azide, when it is treated in water with heat, undergoes a rearrangement. Also, there's a loss of the carbonyl carbon again, but we get back to a primary amine, CO2 plus N2. So there's a loss of dinitrogen in the Curtius rearrangement. And again, you should go and practice some specific examples. You could draw that one with an N3 there instead of an NH2, and we end up at the same place. So how does this reaction occur? This is a very interesting mechanism, and I'm going to illustrate it for the Hofmann. So the Hofmann mechanism. Now, again, just simplistically, we're going to use the minimum number of atoms that we need so that we can avoid drawing lots of extraneous stuff. This is treated and reacts first with hydroxide. So we deprotonate. A reversible reaction. Now, this reacts with Br2. I'm going to push the arrows coming back down from oxygen, swinging out from nitrogen to brominate the nitrogen. Now, we've seen this before in bromosuccinimide, for instance, that we used in radical reactions. So we can make those nitrogen-bromine bonds pretty easily. Now we have an acidic proton again. In fact, we would probably suggest it's even more acidic. Equilibrium there to produce so we have now our key intermediate in this reaction. So now a whole bunch of things happen at one time. So watch closely. As the lone pair from oxygen swings back down, the alkyl group migrates to nitrogen and the bromine leaves. And this is because we've got the bromine. This is all part of a mixing of a normal vibrational mode of this molecule. And so what does that produce? That is an irreversible step, and it puts the methyl group on the nitrogen. Remember, this bond went to here, so the nitrogen still bonded to this carbon, which is this carbon. This is an isocyanate. An isocyanate. Now, under these conditions, of course, hydroxide, I'll remove that, I don't want it to look like a radical, attacks oops, I put the proton on there too fast. Anion that will quickly get protonated by water. Remember, we're under strongly basic conditions. Now, this step I want you to pay close attention to because it's the reverse of how we scrub carbon dioxide from electric generation power plants. We use amines to scrub carbon dioxide out. So this reaction is about to release CO2. So when we have a base, we can pluck off that proton. The electrons can swing around and we kick out the amine. This produces, of course, that amine anion, CO2 plus water, of course. This will very quickly deprotonate water to give us the amine. Now, that it's a bit convoluted, but it's got some very interesting mechanistic details that incorporates all the things we've been learning about carbonyl carbons. Since this was an sp carbon, it becomes an sp2. That's the equivalent of going from sp2 to tetrahedral to form our tetrahedral intermediate. We just started at sp, we go to sp2. Whereas we start at sp2, we go to sp3, that's our tetrahedral intermediate. So there's a commonality here. Now, what happens with the Curtius rearrangement? Well, in the Curtius rearrangement, when we have this, there's another resonance form we can draw for this. And that puts the negative charge on the other end. But what I hope you see is we have dinitrogen ready to go. So you heat this up a little bit, and that lone pair can swing over here to make a carbon-nitrogen double bond. The alkyl group migrates, and nitrogen says, "See you later, alligator." This produces the equivalent isocyanate intermediate. So this is the Curtius mechanism. So it's the key rearrangement produces this isocyanate, at which point we pick up in the same mechanism as before.